This is the third video in the basic HVAC series, written and presented by me, Jean Hvac. Here's the legal stuff. Okay, so we have the idea of an air handling unit, an AHU. And what an AHU does, it's an air conditioning unit, a big one, admittedly, and some of these are pretty big. We're taking air and we're conditioning that air. We're heating or cooling it and we're sending it to the rooms. Typically here in Perth, what we do is we cool the air to 12 degrees Celsius and send that down the ducts to the room. That's because typically in Perth it's hot. So here's the supply air. We call that SA for short. And here's the return air again, RA. Here's the outside air. And here's the relief air. Sometimes we take outside air and we relieve all the air straight out of the building. Sometimes we take some of the return air, we recycle some. And then we mix it with the outside air. Because we always have to have a small amount of outside air, a minimum outside air quantity. That's legally mandated. We have an economy damper here, we call it the economy damper or the mix damper, and we open and close the dampers to mix the air appropriately. Cooling coil and a heating coil. Cooling always before heating, that allows for dehumidification. Sometimes instead of a cooling coil full of chilled water, CHW, we would have a evaporator from a refrigerative system. We would call that a DX system. Sometimes instead of a heating coil full of heated hot water, HHW, we would have an electric duct heater or an EDH. These are VAV boxes. We'll talk more about those later. They're essentially pretty low-tech devices. They're a huge butterfly valve in a duct. The other thing they do is they measure the air flow, so that if a VAV box serves a room or an area, we measure the airflow through the VAV box to make sure that that room gets the correct amount of air. A VAV box is normally also associated with its own temperature sensor. And what we do is we open or close the butterfly valve from the minimum air to the maximum air to supply less or more cooling. Let's look at these dampers. These dampers, they're louvers that you can motorize. They can open or close. Now, traditionally, the way we used to do this, back in the days where we had pneumatic controls, is traditionally all three dampers would be controlled together. Because when you look at it, if you look at the mix damper, the one in the middle, the mix damper closes when the other two open. So all three dampers could be controlled from the one output. Now, that's just not necessarily anymore. We use computers, we use computerized control systems, and these computerized control systems have got loads of outputs. So what we should do is we should have each damper on a separate output. This allows us to control them much more precisely. One of the things we have is that we have to supply an amount of minimum outside air. There's two ways we can do this. We can have a separate minimum outside air damper. That's actually quite a rare thing. Or we can just have the outside air damper kept slightly open. One way that we used to do this is we used to just disconnect the last of the louvers off of the damper, jam it open, and then screw it in place so that it was always open. Now this is just shocking, if not vaguely illegal. It's a terrible thing to do. It doesn't give us any outside air control. It prevents proper control. You can't close the damper ever. It's like having a window propped open all the time to supply outside air. The reason we used to do it, of course, was because in the days of pneumatic control systems we only had one output to all three of the dampers. But now we have separate outputs. We have a computerized control system. There is absolutely no justification for doing this absolutely heinous act. We should have a separate output and control the dampers appropriately. Next problem. We have a separate output and control the dampers appropriately, but we make this assumption that the dampers are linear. In other words, we assume that when you open a damper 50%, you get 50% of the airflow through it. Well, that's not true. That is definitely not true. A damper is basically a butterfly valve and is very, very not linear. In actual fact, they look like this. What this is saying is, by the time you've opened the damper about 20%, you've virtually got all of the air. So if you want 50% of the air, you open the damper about 10%. If you control the system using it as if it's linear, and it's not linear, what you end up with is very, very bad control. So instead of being a mixing control, which will gradually mix outside air and return air, you end up with an on-off control. It's either outside air or return air. There is no reason to continue to treat the dampers as if they are linear. We're not using 1970s pneumatic controllers anymore. We're using modern electronic computerized control. And modern electronic computerized control will very easily deal with a non-linear actuator. What you do is you can just quickly open the actuators to different positions and see how much air goes through. Now in this one what it's saying is when the actuator is 20% open, the 70% of the air volume goes through. So all we do is we program this curve into the computer. And in the computer, instead of, if you want 50% air, it doesn't open it 50%, it opens it 10%. And we will actually get correct mixing of return air and outside air. So here's a graph. We use a graph function. This is Intertech Controls function block. All of the BMS systems are the same. I don't care what any of them say. Anything that uses function block uses function block. Function block is a function block. The only difference between them is the pretty little pictures they print on top of the boxes. This one is using economy cycle, and it's using a graph to convert the economy cycle into the correct damper positions. It's not that hard. It's also using a little minimum outside air to hold the outside air damper open 10% even if we're not using outside air. I'm not going to explain this to you. I think you can work your way around it. The thing is with function blocks, each box does a little job and the signals follow down the lines. There is a course on function block programming which you will find. So, we want to cool the air. We want to cool it as economically as possible. So, which air should we take? We can either take return air coming back from the building, or we can take outside air from outside. Now, you might think to yourself, well, return air, that's already been conditioned. That's already been air conditioned. So it must be cheaper to take that because it'll be cooler. So you'd think that our preference would be to take return air and just put minimum outside air in. But that's not always the case. You see, the problem isn't cooling the air. There's more to the air than meets the eye. There's also water in the air. We call that humidity. So we not only have to cool the air, but we have to cool the water. But wait, there's more. There's only so much water that the air will support, and the amount of water that the air supports is dependent on the temperature. So if we cool the air down, there's every chance that it won't be able to support that water, so that water will condense. When that water condenses, it needs energy to condense, so we have to supply energy to condense it. So let's have a look at some of the energy we need. Let's take the example of, we've got air, and we've got a kilogram of air, and it's 100% humidity. It's supporting absolutely as much water as it can support, and it's at 30 degrees Celsius. To make the numbers easy, I've used round numbers, okay? So I'm going to take air at 30 degrees and I'm going to cool it to 10 degrees. So 100% humidity, I know that 100% humidity at 30 degrees, the 1 kilogram of air supports about 28 grams of water. If I'm going to cool that to 10 degrees, I can only support 100% humidity. At 10 degrees, however, 100% humidity supports 8 grams of water. So I need to condense 20 grams of water out. Let's do some of the sums. Cooling the air by 20 degrees. And there's the sum, and cooling the air by 20 degrees will cost me 20.07 kilojoules. Cooling the water vapour by 20 degrees will cost me 23.41 kilojoules. Condensing 20 grams of water will cost me 45.2 kilojoules. It costs more to condense the water than to cool everything. So all up, taking this 30 degree air, changing it into 10 degree air, condensing out the water has cost me 88.7 kilojoules. Okay, let's have a look see. Now let's take another kilogram of air, this time much hotter, 35 degrees Celsius, and we're going to take this 35 degree air and cool it to 10 degree. The difference is, the big difference is that this 35 degree air is at 50% humidity. Okay, so we're going to take 35 degree air, 50% humidity, and at 35 at 50% humidity contains 18 grams of water. We're going to cool it to 10 degree air at 100% humidity, and that's going to contain 8 grams of water. So 10 grams of water have to be condensed out. Right, let's look at the numbers. Cooling down the air from 35 to 10, that's 25 degrees, cooling that air will cost me 25.09 kilojoules. That's more than before. Cooling the water vapour from 35 to 10, that's going to cost me 18.82 kilojoules. That's again more than before. Condensing 10 grams of water is going to cost me 22.6 kilojoules. So all up, cooling the much hotter air actually cost me 66.5 kilojoules, which is less than before. The reason for this is because I condensed less water out. So what we saw was that even though the air was hotter, because it had less humidity, it was cheaper to cool. If we try and decide, when we're trying to decide which air to use, whether to use outside air or return air, if we make that decision based purely on temperature, then more often than not, we're going to make the wrong decision. We shouldn't use temperature, we should use enthalpy. Remember, enthalpy is the total energy contained in the system. If we look at 1 kilogram of air at 30 degrees, 100% humidity, it has 100 kilojoules per kilogram enthalpy. If we look at air at 35 degrees, 50% humidity, it has 82 kilojoules per kilogram enthalpy. As you can see, the second one has less enthalpy. What this means is the second one will be easier to heat and cool. So when we're making that decision whether to use outside air and return air, we need to make that decision based on the enthalpy of the air, not the temperature of the air. That's particularly important when you consider that return air is nearly always very, very high humidity because we breathe out moisture. In Perth, our humidity is normally around about 40-50%. So if you have return air coming back 100% and outside air coming in 50%, it's nearly always better to use the outside air. And we're not doing that. Quite often in Perth, we also get the rather strange situation where it's cold in the mornings. Then the sun gets up and it's actually warmer outside than it is inside. In these cases, we should actually take the outside air in. So we should effectively do economy heating. Rather than just going on full return air, if the outside air is hotter, we should take that in. Of course, this only makes sense if we're not cooling the air to 12 degrees. So in other words, it only makes sense if we're using set point reset. So economy heating is only sensible if we're using set point reset. It's much simpler doing the calculation because it's based purely on temperature. The biggest advantage of using more outside air is that it improves air quality. Numerous studies have found that using too much recycled air leads to, well, there's several problems. Firstly, an increase in humidity in the air-conditioned space. Increase in humidity tends to lead to damp walls, and that leads to mold. Spores coming off mold, well, I don't even know where to begin. Some of them are so bad. Some of them just make us mildly ill. Some of them make us very ill. And some of them kill you. So mold is a very bad thing in a building. The lack of fresh air makes people irritable. It makes it hard to concentrate. People get irritable, they get angry, they get tired. All in all, this leads to what we call sick building syndrome. And sick building syndrome basically means people just don't like working in the building. It's directly related to the amount of outside air. If we correctly select our economy cycles, both cooling and heating, we give more outside air. We relieve the dampness in the buildings and we make people happier. We also save money. So, this is a function block, once again, inner tech, function block, economy cooling and economy enable. Cooling enable, heating enable, not a complicated thing. I'm just using enthalpy in both cases. The only reason why we wouldn't use enthalpy is because in order to do enthalpy we need to install humidity sensors, and a humidity sensor costs $200. So we'd save $400 on the install. Of course, that money, that would pay for itself in the first month of operation. Let's look in detail at some of the components of the air handling unit. We've looked at the dampers. Let's look at the supply air fan. As the VAVs in the rooms open and close, to vary the air, because remember, we vary the air to cool. So when we want more cooling, we have more air. As they open and close, we need to also vary the speed of the supply air fan. If we don't do this, then what's going to happen is there's going to be too much velocity at the VAVs and they'll whistle. Also, we stand a very good chance of overpressurizing the ducts. So we need to moderate the supply air fan, or the supply air fan flow. Couple of ways of doing this. In the olden days, we would use a thing called an inlet guide vane, which was basically a louver where we choke off the inlet to the fan. It's very inefficient. If we had a propeller style fan, then we could feather the blades. Still not efficient, because you see, we're still putting the energy in to drive the thing round and round. We're just not using that energy. A much better solution is the variable speed drive, the VSD. VSDs have been around for about 20 years. Well, no, what am I saying? Maybe 30 years. What this does is it varies the frequency to the electric motor and therefore varies the speed of that electric motor. The thing that makes the VSD so attractive is the equation which states that the power is proportional to the speed cubed. What this means is that if you halve the speed of the fan, the kilowatts don't reduce by 50%. The kilowatts reduce to an eighth. So when you halve the speed, you reduce the kilowatts to an eighth. The problem with the VSD, the downside of the VSD, is that in order to achieve this frequency change, they actually use radio frequency. So we must use screen cables when we connect a VSD to a motor. If we don't use screen cable, then we'll find the communication starting to fail all around the plant. So here's a very simple supply air fan static pressure control. Remember, we take the static pressure as far away as we possibly can from the fan so that we don't worry about system effects or basically an unpleasant pressure profile because we're somewhere near the fan or the cooling coils or whatever. So we take the static pressure, we put it into a PID loop. I'm not going to go into PID right now, and that output of the PID will control the VSD. There are occasions where we need to draw the air back out of the building, so we use a return air fan. Typically, a return air fan is a propeller type fan because we're now talking about quite large volumes and low pressure. So we need to vary the speed of this. Once again, we could feather the blades of the propeller, or much better, we control it using a VSD. We need to maintain a very slight positive pressure in the air-conditioned space. The reason why we want a slight positive pressure is so that things like smoke, pollution, flies, etc. are kept outside of our building. It needs to be a very slight positive pressure. If you get it wrong, either you end up with a negative pressure or you end up with too high a positive pressure, then you're going to get trouble with the doors and windows, especially revolving doors. The revolving door will start turning like a wind turbine, and they can build up quite a lick of speed. So we need to maintain a very slight positive pressure. Now there's three ways we can do this. The best way is to actually measure the pressure in the space and maintain it. An alternative is to measure the volumes that we're supplying and the volume that is returning and make the supply volume slightly more. Another alternative is simply to ratio the two fans so that you run the supply air fan at say 98% and you ratio the return air fan to say 96%. So here are function block diagrams for those three different ways of controlling. As you can see, they're function blocks, nothing too complicated there really. Okay, now I want to control the temperature of the supply air. That's the air leaving the air handling unit. There's two ways I can do this. The first way is I can use the dampers. I can use the dampers to mix in the return air and the outside air, because remember they're going to be at different temperatures. So the first way of controlling temperature is just a kind of a passive way, just by mixing in air of different temperatures. The next much more active way of heating or cooling is to use the chill water heat exchanger and a chill water valve and the hot water heat exchanger and the heated hot water valve to modulate those two valves to heat or cool the air. Okay. So I have chill water, CHW, chill water valve, and I have heated hot water and a heated hot water valve. This little diagram is supposed to explain how we would open those valves. Now, on the horizontal axis, we have a value which we call the percentage loading. All air conditioning equipment produces a value which is called the percentage loading. The percentage loading tells you how hard it's loading, or in other words, how hard is it trying. 0 to 100% is cooling. So 100% is it's trying as hard as possible to cool. 0 to minus 100% is heating. So as it goes into the minuses, it's trying harder and harder to heat. The vertical axis, in this case, shows the valve position. And what we're saying is that from about 5% to 100%, we open the valve, the chill water valve. And from minus 5% to minus 100%, we open the heated hot water valve. There's a little space in between 5% and minus 5%. We call that the dead band. In the dead band, we don't do anything. We say, we're not actually trying very hard to heat or cool, so don't do anything. It's important to have a dead band. If you don't have a dead band, then you stand the chance of oscillating, hunting wildly between cooling and heating and cooling and heating. So the dead band stops you. The wider the dead band, the more economical the entire system is. Because the wider the dead band, the less we actively do anything, and the less we actively do anything, the less money it costs us. So, we're stuck with, I did mention earlier, this little box which I called PID. PID is a kind of a magic little box. You put two things into it, a set point and a process variable. The set point is the target we're looking for, and out of it comes a control. Problem you have with PID is most PIDs are not symmetrical. In other words, they won't symmetrically control up and down. So we shouldn't use the same PID for heating and cooling. What we should do is have two separate PIDs, one for heating and one for cooling. HVAC PIDs are rather different than normal PIDs. HVAC PIDs, they are slightly modified PID, which either comes with two separate outputs, direct output, for cooling, reverse output for heating, or they allow you to have a range which goes from minus 100 heating to plus 100 cooling. So here's your standard PID. Once again, you have two inputs, a set point, which is the target we want to reach, and a process variable, which is the thing that we're controlling. And out of the PID comes a valve position. For now, let's just treat it as a magic little box. We'll be doing PID later on in the course. This is a slightly more complicated diagram. Now with this diagram, the initial cooling, for the initial cooling, I'm using the dampers. I'm mixing in the two different temperature airs. So from say 0 to 30% of economy of loading, I will use the dampers. I call that economy because I'm using air. I'm using passive things to cool. I don't have to pay for air, it's just there. And then after say 30-40%, if the cooling from wherever I'm getting it isn't sufficient, then I'm going to use the chill water valve. In the event of the outside air not being available for cooling, then what that means is the deadband just gets bigger. Well, I can live with that. It saves money. But remember I said sometimes in Perth, the air outside is sometimes warmer than the air inside the building, and when we're trying to heat. So I can also do economy heating. In this case, I will use the outside air to heat to a percentage loading of about minus 30, minus 40%. After that, if it's not able to heat enough, then I'm going to start using the hot water. If outside air isn't available for heating, then once again my deadband just becomes bigger. I'm pretty sure I spelled economy incorrectly there, on economy disable. It's too late to change it now. Anyway, my deadband just becomes bigger. Once again, I'm just saving money. Here's the total temperature control with correctly modulated dampers and everything. It's not too complicated. If you want, you can stop the video and go through it. But I will be going through I'll be writing an entire program in a later video. Sometimes, instead of having a hot water coil with heated hot water, we've got electric heaters instead. Electric duct heaters, EDHs. In this case, I have two stages of EDH, and I'm switching these two stages in. Remember, with an electric duct heater, it can either be on or off. There's no in between. What this diagram is showing is that stage 1 heating will come on around about 60% and will stay on until it drops to around about 40%. Stage 2 heating will come on if around about minus 90%, but stays on to about minus 60% by the look of it. Okay, so that's two-stage EDH. And remember, with an electric duct heater, it's either on or off. We call this two-position control, or sometimes differential control, or hysteresis control. But wait, somewhere else in the course I told you about pulse width modulation. Pulse width modulation, effectively, it's a dimmer switch for a heater. Just like a light can only be on or off, we can use a dimmer switch, and what a dimmer switch does is it flashes the light so quickly that we don't realize that it's flashing, and it flashes it so that it doesn't look like it's fully on. That's called pulse width modulation. We can do the same with a heater, and when we pulse width modulate control a heater, we're not restricted to on or off. We can make it 5%, 10%, 18.7%, whatever we want. So this is two-stage heating, but with pulse width modulation. With pulse width modulation, we can turn the heater to 37%. We get much finer control. Traditionally, in Perth, we control our room set points to 22.5 degrees. The reason we do this is because although 23.5 degrees is the ideal temperature for Perth, 22.5 degrees is the ideal temperature if you're wearing a jacket and tie. So we traditionally control our set points to 22.5. It's been said that every 1 degree is a 15% saving in energy costs. So we're basically wasting 15% of our energy because some of the people in the office wear a jacket and tie. Stupid, really. But even more stupid is the fact that we don't actually like 22.5 degrees all year round. You see, your body changes according to the seasons. If it's hot outside, if it's the middle of summer and it's 40 degrees outside, your body is looking at this and thinking, it's hot, I'm expecting to be warm. So if it's 40 degrees outside, 26 degrees will seem cool, very cool. 22 degrees will seem cold, unpleasantly cold. Similarly, if it's the middle of winter and it's 0 degrees outside, 18 degrees will seem warm, pleasantly warm. 22 degrees will feel unpleasantly hot. So, rather than using 22.5 degrees all year round, what we should do is reset our space temperature set point. We should, when it's 40 degrees outside, we should have a set point of 26. When it's 0 degrees outside, we should have a set point of 18. At very least. This will save masses and masses of money. And it'll also make everybody in the building more comfortable. Similarly, the entire concept of having an air handling unit which sends out 12-degree air all year round is ridiculous. What we typically have to do is we send out this cold air in the middle of winter and then we heat it back up using electric duct heaters at the VAVs. Well, that's ridiculous. What we should do instead is we should ask the VAVs, how are they doing? Remember, we have computerized control systems nowadays, and these computerized control systems are all networked together. So the air handling unit controller can talk to the VAV controllers and ask, hey VAV, how's it going? What are you doing? Are you heating or are you cooling at the moment? And the VAV will respond and it will give a percentage loading. And the percentage loading tells us how hard the VAV is trying to cool, 0 to 100, or how hard the VAV is trying to heat, 0 to minus 100. What we should do is, if the VAVs are all trying very, very hard to cool, their percentage loadings are all 100%, then we should send them cold air. We should send them 12-degree air. If they're all trying madly to cool, we send them 12-degree air. If they're not trying madly to cool, then we don't need to send 12-degree air. We maybe can send 14-degree air, 15-degree air. Every time we let that air get a little bit warmer, we save money. And every time we let it get a little bit warmer, there's more chance that we can use outside air. And if we can use outside air, we save more money and we make the people in the building happier because they get fresh air. If it's the winter time and the VAVs are all got their electric duct heaters on, they're all madly trying to heat, Well, it just makes no sense to send them cold air. We should be sending them warm air. If anything, we should be trying to heat centrally, or not, at very least, not cooling. If we just don't cool the air, then we save a fortune. Once again, this also increases the chance that we can use outside air. So, resetting the supply air set point will save us bundles and bundles of money, and also it saves the environment because we're using less energy, we're creating less carbon. Other things to consider when we're controlling. Our air handler is sending out the air. It's sending out air to zones. These zones switch on or off depending on their schedules. There's going to be start-stops. There's going to be holidays. There's going to be lunch times. By carefully selecting our start-stop times, by carefully setting up our time schedules and our holidays, we can make sure that we don't condition an area when there isn't anybody in it. For instance, I'm working in a TAFE right now. We air condition all our classrooms all the way through lunchtime. Well, there's no students in here at lunchtime. We condition all our buildings through till about 5 o'clock. Well, 4:30, the doors open and the students leave. Whoosh, they're gone. So we can just save. If we can just turn the air conditioning off for 1 hour at lunchtime, that's 1 hour in 8. That's better than 10%. A 10% saving in energy, a 10% saving in our cooling and heating bill. That's pretty significant. Some places, you always have to bear in mind, need to work on a 24-hour schedule, and there needs to be some sort of way of doing this. Police stations, hospitals, they work on 24-hour schedules. Don't forget them. It makes sense to construct the air conditioning system such as the 24-hour zones come off a different air handler from the 9 to 5 zones. That way, we don't have to run the entire air conditioning because we have a few 24-hour zones. Remember that there's always people working somewhere. Even when the office staff go away, there's going to be security people. There are going to be cleaners there. We need to think about supplying air to those people. Maybe there should be some sort of override system to allow air for the cleaners. One way we quite often do this is by having what's called an after-hour push button. You basically push the button and it turns your air conditioning and your lights on for an hour, say. And then typically we'll flash the lights to let you know that it's just about to switch off, and you go and push the button again. Some of them work, you push the button on and then you push the button as you leave. The problem with that is that nobody ever pushes the button when they leave. So I always prefer to put a timer on them. Once again, you need to think about this. We need to construct the system such that we don't have the entire building's aircon come on because one person is working after hours. In the evenings, when the building is empty, we talk about occupancy. We talk about the building being occupied and being empty. So we talk about having occupancy and not having occupancy. So, when we don't have occupancy, there's a couple of things we can do. We could just turn the air conditioning off. Or we could go into what's called nighttime setback. Two ways this can work. We continue running the air handling unit, but with much changed set points. So the cooling set point is much higher, the heating set point is much lower. That way, hopefully, we don't have to heat or cool. This is effectively what happens in some hotel rooms, so that the hotel room isn't actively heated or cooled to normal occupancy temperatures, but it doesn't get really, really unpleasantly hot or really, really unpleasantly cold for when somebody walks in. Another alternative is that we don't run the air handler. What we do instead is we monitor the outside air temperature. And we only run the air handler, once again probably to setback values, if the outside air temperature goes way beyond, or also the space temperatures. We monitor the space temperature and the outside air temperatures, and we only turn the air handler on if either the space temperature or the outside air temperature go well outside acceptable limits. A system which is becoming increasingly popular is evening and night purge. If we're in the situation where we're unable to use outside air during the day because it's just too hot or too humid, then we can use what's called night and evening purge. What this does is, it works on the principle that at night time, the air gets a lot cooler. So what we do is, at night time, when the building isn't occupied, when the building is empty, we effectively purge it. It's like you open all the doors and windows and just let the air blow through the building. Now, we do this, instead of opening the doors and windows, we use the air handlers. We open up all the air handlers to full inlet, much more than we would normally. And then we'll use full outlet. We'll also, in many cases, use smoke exhaust fans to suck the air out. So we'll basically flush the whole building with fresh outside air. Now, the next day, the building is full of fresh air, which is cool because it was cold during the night. The whole building is full of cool, fresh outside air. They're actually starting to build some buildings that do this naturally with chimney structures and return air ducts all the way up the building that will do this without any active fans being needed at all. Draw air through, say, the car park and straight out through the building. Traditionally, the building manager would potter into the building around about 6 o'clock in the morning and turn the aircon on. The reason he did this is because he wanted it to be nice and pleasant when all the workers arrived at 8 o'clock in the morning. So he would turn the building on early so that it was nice and pleasant when they got there. It was either warm enough or cool enough. Now, this is taking the example of a cold building. So the building manager totters in at 6 o'clock in the morning, turns the building on to warm it up so that it's 22.5 when the people arrive. We don't need to do that anymore. We've got control systems. We've got computers now. What we should do instead is what's called optimized start. What optimized start does is you enter a value which is the thermal capacity of the building. Basically, how fast does the building heat up or cool down? And then the optimized start looks at the outside air. And it looks at it and it says, okay, the building heats up at, say, 10 degrees an hour. So if the outside air is 0 degrees, and I want to get to, and I'm not going to go to 22.5, I'm going to say I want to get to 20. So slightly less than set point. So I want to get to 20. It's 0 outside, so at 10 degrees an hour, I need to start the building 2 hours early. So it starts the building at 6. But if it looks at it and says, oh, it's 10 degrees outside, so I only need to start the building at 7. We just saved an hour. Or it looks at the outside and it says, oh, hang on, it's 20 degrees outside. I don't need to start the building until 8. We saved 2 hours. If we do this, on average, we'll save at least, on average, 50% of the startup time. If your startup time is 2 hours, I just saved an hour. 10% of my air conditioning bill. Optimized Start is built into every BMS system, building management system I have ever worked on, has got Optimized Start built in. You just need to switch it on to save 10% of your air conditioning bill. And then you've got Optimized Stop. Traditionally, we'll run all of the building, all of the air conditioning, right up until the end of occupancy. Let's say 5 o'clock, all the office workers go home. So we run everything through till 5 o'clock. We don't need to do that. We need to keep giving them air, yes we do, but we don't need to keep giving them necessarily cold air. In order to make cold air, we need to make cold water. And in order to make cold water, we need to run chillers. Chillers are great big refrigerators that make cold water. What we can do is, we can look at the outside air temperature, look at the inside air temperature, and we can say, oh look, the building warms up at 10 degrees an hour. If we want it to be just a little bit above set point for 5 o'clock, if we want it to be, let's say 32 degrees at 5 o'clock when they leave, it'll be a little bit unpleasant, but then they're leaving anyway, who cares? If we wanted it to be, let's say 32 degrees, if the building heats up at 10 degrees an hour, I could turn the chillers off an hour early. In fact, there's a whole mass of chill water in the pipework. I could probably turn the chillers off 2 hours early. The chillers take a lot of energy. They're probably 30-40% of the energy bill of your air conditioning. If I can turn those off 2 hours early, and nobody minds, then that's money in the bank. That's also, of course, greenhouse gas that we're not creating. That's also, of course, saving the planet. This is easy to do. It's called Optimized Stop. It's where we coast into the end of occupancy. It'll cost nothing. It'll save a fortune. Another thing to look at is aspect. Aspect is which way is the building facing. Now, here we have a building and it's facing, well, there's one side of it is facing north. Well, let's say it's facing east and the sun is rising. So the east side of this building is going to get very hot because the sun rises. The west side of this building is going to get very cold because it's in shadow. Traditionally, we would have 2 air handling units on the roof. Let's say I've got 2 air handling units on the roof. One air handling unit is handling the east side and one air handling unit is handling the west side of the building. The east side of the building is getting really, really hot. So we're taking hot air away from the east side because the sun is blazing in through those windows and those windows are getting hot. They get hot very quickly. So we're taking hot air out of that, we're madly cooling it in the air handling unit and we're sending it back to the building, to the east side of the building. In contrast, on the west side of the building, we're madly taking cold air because it's cold, because those windows are getting cold, because they're single glazed windows, because we live in Perth and we don't know what double glazing is. So these single glazed windows are bloody cold. We're taking cold air out of that building. We're heating it up like crazy, and we're sending it back to the building. So I've got two air handlers. One's cooling, one's heating. I've got the chillers running. I've got the boilers running. How about this then? Instead of doing that, we simply move the air around. We take the air from the hot part of the building and we send it to the cold part, and we take the air from the cold part of the building and we send it to the hot part. It's very easy to do, just a few changes in ductwork, and this will do. In many cases, this will mean that we don't actually have to actively condition any of the air. We take the air which is heated by the windows and we send it to the cold part of the building. We take the air which is cooled by the windows and we send that to the hot part of the building. This costs nothing. If we can't change the ductwork, then we could use heat exchangers. I mentioned earlier when I was talking about wheel heat exchangers, some of these heat exchangers are 80 or 90% efficient. Heat exchangers are passive. They cost us nothing. And yet they save a fortune. They should be mandatory. But the effect of her being on those around her was incalculably diffusive. For the growing good of the world is partly dependent on unhistoric acts. And that things are not so ill for you and me, as they might have been, is half owing to the number who lived faithfully a hidden life and rest in unvisited tombs. The end.